So when we look at thermochemistry, there are different ways to calculate delta H, and also with knowing delta H, there are ways to determine the amount of product to produce or reactant consumed by how much heat is released from the reaction. Or if we have a certain amount of product or reactant, we can calculate how much heat is needed to produce that much of that product or reactant. And so what we have to learn here is we want to know how much heat is needed to produce 5.2 kilograms of CO2. So here is CO2, and it tells us the delta H for this reaction is negative 2050 kilojoules per mole. And so the first step is we need to show that for every 4 moles of CO2 produced, we generate 2050 kilojoules of heat. So what we want to do is find out what this ratio is for 1 mole of CO2. And so we divide both sides by 4, and we get the amount of heat produced by 1 mole of CO2. Now what we're going to do is we're going to take the mass of CO2, convert it into moles, and then now that we know that 1 mole of CO2 generates this much heat, we can determine how much heat is generated by 5.2 kilograms. So we convert the kilograms to grams, divide by its molar mass, we get that there's 118.2 moles of CO2. So now the heat of the reaction is equal to the delta H times the number of moles, in this case negative 512.5 times 118.2, and we get negative 60,600 kilojoules. So that's how much heat is needed to be produced in order to form 5.2 kilograms of CO2. So in the second example, here we're given another combustion reaction. It gives us the delta H of reaction. Wants to know what's the mass in kilograms of H2O produced when 6.7 times 10 to the 6 kilojoules is released. So this reaction releases 6.7 times 10 to the 6 kilojoules. How much H2O is produced in kilograms? So again, when we look at the reaction, we see that 14 moles of water have a delta H of 4,651. So again, we set these equal. We know that for every 14 moles of water, we produce this much heat. So then we want to find out how much heat is produced by 1 mole, which is 332.2 kilojoules. Now that we know how much is produced by 1 mole, and we know how much total heat was released, we can calculate the moles of water that was produced. And so the Q of reaction is this 6.7 times 10 to the 6. The delta H per mole of H2O is 332.2. And so we can solve for the moles of water. So notice that the negative signs cancel out. So since it says that it's released, it's understood that it's a negative quantity. We find the moles of H2O. Now we can multiply by the molar mass. We get the grams. We divide by 1,000 to get kilograms. So it's about 36.3 kilograms of steam is produced when we release 6.7 times 10 to the 6 kilojoules for this reaction. So in the last two problems was dealing with thermochemical stoichiometry. Here we want to know the delta H of a reaction given a series of reactions. So the delta sign got deleted here, delta. Okay. So we have this reaction, the synthesis of dinitrogen pentaoxide. We want to know the delta H of this reaction, and we're given 3 reactions or 3 equations where the delta H is known. To determine the delta H of the equation for the synthesis of dinitrogen pentoxide. So there are many different ways to approach this. I'm going to approach it one way, but if you did it a different way and we come to the same conclusion, no problem. So what I like to do first is, in the equations given to us, we want to make sure that in the equation we want, the reactant or product is on the correct side. So what do I mean by that? So here in the equation we want, nitrogen is a reactant. In the equation given to us with nitrogen, nitrogen is a reactant. In the equation we want, O2 is a reactant. In the equation given to us, O2 is a reactant. N2O5 is a product in the equation we want. In the equation given to us, it's a reactant. So when you're dealing with what's called Hess's Law, one thing you can do is you can flip an equation which changes the sign. So if I do that, I flip the second equation because I wanted to put N2O5 as a product. So now we've done all the flipping that needs to be done. Next, we want to look at the coefficients. And so in the equation we want, nitrogen has a coefficient of 2, oxygen has a coefficient of 5, and N2O5 has a coefficient of 2. So what we want to do is we want to change the coefficient of N2O5 into 2 and change the coefficient of N2 into 2. So here we multiply this reaction by 2, including the delta H, and we multiply the third reaction by 2, including the delta H. Because we want to make the coefficient of N2O5 2 and the coefficient of N2 2. Now O2 don't worry about yet because it'll work itself out. So now when we do that, we get this. Notice that the delta H increased by 2 for both those reactions because you have to multiply the delta H by the 2 as well. And so now you'll notice here that the way we have it set up, we have 6 moles of O2, 7 moles of O2 on the reactant side, and we have 4 moles of H2O on the reactant side. And the H2O doesn't cancel out, and we have too many moles of oxygen. We want 5. So the next thing we're going to have to do is we're going to need to flip the first equation so that the water cancels out. Because right now the water doesn't cancel out, and you see in our equation that we want, water is not there. So what we're going to have to do is we're going to have to flip the first equation. So we flip it and we change the sign. So now everything should be lined up that we can start crossing out similar species on both sides of the reaction. So for example, 2H2O on the reactant side cancels out with 2H2O on the product side. 4HNO3 cancel out with 4HNO3. 2H2 on the product side cancels out with 2H2 on the reactant side. Now what we have left is we have 6O2 on the reactant side, we have 1O2 on the product side. So that's going to cancel out, and now our oxygen is going to change to 5, which is what we want. So now we've canceled out everything we don't need. So when we add it together, we get the delta H of the reaction. So when you add them, you just add the delta H's just like they are. So 57.16 or 571.6 plus 147.4 minus 696.4, whatever you get, you put there. So we just simply add up the individual delta H's to get the delta H for this reaction. So here we're given the following equations with the delta H values determined, and we want to determine the heat of reaction for this reaction involving oxygen difluoride and sulfur to produce sulfur dioxide and sulfur tetrafluoride. So again, what we want to look at is in the equation given to us, we see that OF2 and sulfur are reactants. So in the equations that we know the delta H for, we want to make sure that OF2 is a reactant, and it is. And we want to make sure S is a reactant, it is. Then we want to see that SO2 and SF4 are products. Well, here in the second equation, SF4 is a reactant, so we're going to need to flip the second equation, and we see here SO2 is a product. So the only thing we need to do in regards to flipping is to flip the second equation. So when we flip, we change the sign of delta H. So it went from negative 827.5 to a positive 827.5. So we've done all the flipping we need to do. Now we've got to work on the coefficients. So in front of OF2, we have a 2. In front of sulfur, we have a 2. But in the equations with OF2 and sulfur, we have a 1. So we're going to need to multiply these two equations by something to make it a 2 here instead of a 1. So we're going to multiply both of them by 2. Now for SF4 and SO2, they should have a coefficient of 1. And for SF4, it does have a coefficient for 1. For SO2, since we have some on the reactant side, some on the product side, this should work itself out if we do the right multiplication. So for the second reaction, we don't need to multiply anything because SF4 needs a coefficient of 1 and has a coefficient of 1. So now we multiply everything by 2, including the delta H. So now we have 2OF2, and the delta H has been doubled. We don't do anything to the second reaction. And the third reaction, we now see that sulfur has a coefficient of 2, and the delta H has doubled. So now we've got all the coefficients set. We've got everything on the correct sides of the equation. We can start marking off similar things. So the 2H2O cancel out. The SO2 here cancels out with one of the SO2s. So we have one SO2 left on this side. So there's one left there. And then the 2O2 cancel out, and the 4HF cancel out as well. And so what we have left is the equation we want, and we just add up these delta H's to get the delta H of this reaction. So here we have another reaction we want to know the delta H for. Methane and ammonia react to give hydrogen cyanide and 3H2O. It gives us this series of reactions. So again, we notice CH4 is a product in the reaction we want, in the reaction given to us. Excuse me, it's a reactant in the reaction we want, in the reaction given to us, it's a product. So we're going to have to flip the second equation. Next, NH3, it's a reactant in the equation we want, in the equation given to us, it's a product. So we're also going to flip NH3 equation. HCN, or hydrogen cyanide, is a product in the equation given to us. Hydrogen cyanide is the product. So the first thing we're going to do is we're going to flip the first two equations, and notice that their delta H's change signs. The third equation we don't need to flip because hydrogen cyanide is on the correct side of the chemical equation. Now we need to look at coefficients. So for methane, we have a coefficient of 1. In the equation with methane, it has a coefficient of 1, so that's okay. Ammonia we need a coefficient of 1, and the equation given to us, it has a coefficient of 2, so we're going to have to multiply by something to get rid of the 2. For hydrogen cyanide, we need a coefficient of 1, and the equation given to us, it has a coefficient of 2. Now for the H2, since it occurs in multiple equations, H2 should work itself out if we did everything else correctly. So we're going to multiply the first and third equation by 1/2. And so when we do this, we notice that now delta H has been reduced by 1/2. So we get this. So notice now ammonia has a coefficient of 1, hydrogen cyanide has a coefficient of 1. So we can start crossing out like terms. So the 2 nitrogens, they cancel. There's a 1/2 on the reactant side, 1/2 on the products. The 2 carbons cancel. Now for the hydrogen, notice that there is a 1/2 of a hydrogen on the reactant side, and there are what we call 7 halves of hydrogen on the product side. Remember, 2 can also be written as 4 halves. So 4 halves plus 3 halves is 7 halves. So 7 halves minus 1/2 is 6 halves. So the 1/2 hydrogen cancels out, and we're left with 2 over 2, which is 1. So that adds up to a total of 3 hydrogen. So now we can add it together, and we get delta H of 256. All we do is we take all the individual delta H's and add them up to get the overall delta H. And so again, we have to cross out what is not needed in the overall equation. Now, if something didn't cross out, that means we have done something wrong in the process leading up to the overall equation. Zoom recording. And the last example, here we have a combustion reaction involving ammonia to produce nitrogen monoxide and steam. We're given these 3 equations to determine the delta H of this combustion reaction. So again, we're going to look at ammonia in the equation we want. It's a reactant. In the equation given to us, it's a product. So we're going to have to flip the second equation. O2 is a reactant. In the equations involving O2, they are reactants. NO is a product. The equation with NO in it is a product. And then H2O is a product. In the equation with H2O, it's a product. So the only equation we have to flip is the second equation. And when we flip it, notice that the sign of delta H has changed. Now we got to work on the coefficients. So for ammonia, it has a coefficient of 4 is what we want. In the equation that we have ammonia, it has a coefficient of 2. So we're going to have to multiply this reaction by something to turn 2 into 4. Now for O2, don't worry about that right now because it occurs in multiple equations. If we do everything else right, it should work itself out correctly. For NO, we need a coefficient of 4. What we have is a coefficient of 2. So we're going to multiply the first equation by some number to turn 2 into 4. And lastly, for water, or steam, I should say, we need a coefficient of 6. In the equation given to us, we have a coefficient of 2. So again, we need to multiply the third equation by something to turn 2 into 6. And so we're going to multiply the first equation by 2, the second equation by 2, and the third equation by 3. And we're doing this so that all the coefficients are set to what we want in the overall equation. So when we do this, first equation we multiply by 2. Notice that the delta H is also multiplied by 2. Second equation is multiplied by 2 along with the delta H. And the third equation is multiplied by 3 along with the delta H. So now we can cross out like terms. So the 2N2 cancel out on both sides. The 6H2 cancel out on both sides. And notice here we have 3O2. We have 2O2 on the reactant side. That's a total of 5 moles of oxygen. So that's correct. So now we can sum them up and add everything up to get delta H. And so here delta H is a negative 1,628 kilojoules. So it should be kilojoules here. Kilojoules per mole. Again, we're doing the same process. The first step is to make sure everything's on the right side or on the correct side of the equation. The second step is to make sure everything has the right coefficients.